So, in this video, we'll recap some stuff we've done, talk about basic notation as about matrices as functions, and 2x2 matrices, 3x3 matrices, and a general example. So, what we know how to do now is we can multiply vectors by matrices, and we know that the reduced row echelon form can tell us about whether or not vectors are linearly independent and whether or not a vector is in a span of a collection of vectors. And so we use these ideas to talk about functions defined by matrix multiplication. So some basic notation: M is an m by n matrix, V is an n by 1 column vector. Then you can multiply M times V. And this is a function that takes an n-dimensional vector and turns it into an m-dimensional vector. So it's a function from n-dimensional space to m-dimensional space. The domain is everything in the n by 1 column vector, so Rn. The codomain is the set of all n by 1 column vectors, and so that's Rm. The range is not the same thing as the codomain. It's the collection of all vectors in the codomain that are images of vectors in the domain. So we'll talk about that a little bit in example 1. Usually we use V for the domain variable and W for the codomain variable. So we have M times V equals W. Input is V, output is W. This is paralleling the use of X and Y. X is input, Y is output, V is input, W is output. So domain, codomain, and range. When we're thinking about Y equals X squared, of course, this is the famous basic parabola. It looks like that. So the domain, that's all the X-axis. The range, the codomain, that's my Y-axis. So the functions generally take x's and turns them into y's, right? So if we take x equals 2, we'll go up to the graph, and then we go over to the y-axis, and that gives me my output is 4, so codomain. But there's nothing down here, right? If I take -3, there's no x value that gives me that. So the actual range is y greater than or equals 0. So the range is all the y's that you get by starting on the x-axis and going over to the y-axis using this function. So the codomain is generally bigger than the range. Doesn't have to be, but sometimes it's the same. But they're different concepts, right? The codomain is the space you're going into. The range is the part of that space that you actually get to. So 2x2 matrices. Here's a 2x2 matrix that we'll use that to explore some basics of the function. So how do we map this sort of thing? This requires 4 dimensions, 2 for a domain and 2 for a codomain. So what's W? I guess W0 equals MV0. So V0 is this particular vector. So we're going to take -3, 0, 0, 1/2 times the vector 1, 2, because that's V0. And what do you get? -3 times 1 plus 0 times 2, right? So this row times this column. And then the second element is this row times this column. So 0 times 1 plus 1/2 times 2. You get -3, 1. So we sketch our domain, put a little arrow in there for our function, W equals MV, and then we draw our codomain. And again, we can't draw a graph like we do for y equals x squared because we need 4 dimensions. It's hard to draw. So if we take 1, 2, 1, 1, 2, this is our vector V0 in the domain, and it gets mapped to the vector 1, 2, 3, 1 in the codomain. And that doesn't actually tell us a whole lot, right? I mean, it's plotting a point. One of the things we want to get away from is understanding functions by plotting points. We want to understand more functions in sort of more general terms. So what we're going to do is we're going to look at m times I and m times j. So remember that when we're in we'll do the calculations first. Our matrix is up there, -3, 0, 0, 1/2. oops, I need to get out of that. So m times I, vector, minus 3, 0, 0, 1 half times I, which is 1, 0. And what's that equal to? Minus 3 times 1 plus 0 times 0, that's minus 3. 0 times 1, 1 half times 0, that's just 0. And what's mj? That's same matrix times 0, 1. 3 times 0 plus 0 times 0. So first entry is 0. 0 times 1, 1 half times 1. Second entry is 1 half. Excellent. So we do want to point out here that m times I and the first column are the same thing. M times j, right, and the second column are the same thing. So this is the image that you get under the function of m times I. This sort of lives in the codomain. This also lives in the codomain, is the image of m times j. So if we take, here's I, here's j, they're a nice basis for my domain. And what does our function do? It takes us over to minus 3, 0. This is m times I, and 0, 1 half. That's m times j. And we know by looking at those two things, of course, that they are linearly independent. There's two of them in two-dimensional space, so they're basis for my codomain. So why is this a useful thing? Well, if we look at our vector v0 is 1, 2. And what is that? That's 1 unit in the I direction and 2 units in the j direction. That's our vector v. So what's m times v0 going to be? That's the image over here. We know that it's going to turn out to be minus 3, 1 because we calculated that. So I'm going to end up with something here as the image. But m times v0, you look at that, that's going to be 1 times mi plus 2 times mj. This is a height of 1 and a length of minus 3. And these coefficients are actually the same coefficients that we have over here. That's not a coincidence, because mv0 is m times 1, 2, which is m times the quantity 1 times I plus 2 times j. Right? That's what we figured out over here. And then we can use the property of matrix multiplication. This is m times, let's go wait over here, m times I. So m times I, and we'll distribute, plus m times 2j. And the last property we need is that we can take the 2 outside of the multiplication, 2mj. Great. So what does that mean? We start with a vector in the basis as coefficients 1 times I plus 2 times j. In the codomain, it's got 1 times the image of I plus 2 times the image of j. Essentially, what the matrix does is it replaces this with mi, that's the first column, and this, the j there, with m times j, which is the second column. So the columns are actually the span over in the codomain. So if k1, k2 is a vector, we can generalize this a little bit. M times k1, k2 equals what? Well, we know the vector k1, k2, k1 is its x-coordinate, and k2 is its y-coordinate, so we can rewrite it like this. What's m times ki plus k1I plus k2j? Well, it's m times k1I plus m times k2j, right? Because you can distribute the m. And then we can take the k's, the k1 and the k2 out. So it's k1 times mi plus k2 times mj. So what a matrix does, basically, is if you express our vector k1, k2 in terms of the basis I and j, the matrix, essentially all it does is it replaces the I by m sub I, replaces the j by m sub j, and remember that this is the first column of the matrix, and that's the second column. And so it turns the linear combination of I and j into a linear combination of the first column and the second column. And so what we want to know then is, are the columns of the matrix linearly independent? Are they dependent? Do they span? All that kind of stuff. So for this particular function, right, where we're multiplying by minus 3, 0, 0, 1/2, geometrically, you take I to be the usual unit vector there, j to be the usual vector there, and if v is any vector that we can represent as being k1I plus k2j, k1I is the x component here, k2j is the y component. What does this function do? Well, this function itself takes I, flips it over the x-axis and makes it 3 times as long. So mi, and it takes j and it gets it in half, right? This is length 1, m times j is length 1/2. This way. This is m times j. So what does it do to this vector? Well, we keep the k1 and the k2, but now the k1 is being multiplied by a vector that's 3 times as long, pointing in the opposite direction. So we go out 3 times as far in this direction. And the k2 now, k2 times j, that's being multiplied by mj, which is a half as long. So we just go half as far in that direction. And so what's our resulting vector? Is this, which is k1, same coefficients, mi plus k2 mj. So geometrically, what's going on? You take any vector, you flip its x component over the y-axis and stretch by a factor of 3. And in the y component, you cut the y component in half. And that's what it does to each and every vector in the plane. Since mi and mj, we can tell, are linearly independent, and there's 2 of them, they span the entire codomain, which is I2, and the range is the span of those 2, because every vector is in the range is a linear combination of these 2 things. So what we've got a function that takes the plane to the plane, takes every vector, flips it over the y-axis, stretches out its x component, shrinks its y component. So here's a vector that's in the codomain. So domain, codomain, and it's 18 minus 2. So we'll call that 18. The minus 2 would actually have to be kind of small. 18 minus 2, this is W1. What's the vector in the domain that corresponds to that? Well, here, right, this is the vector m times j minus 3, 0. This is the vector m times j. This is mi. Right, and so what does this mean? Well, this is I, this is j, and this vector is minus 6 times this one times minus 4 times this one. If we look at this, minus 6 times minus 3 is 18, minus 6 times minus 2, minus 4 times 1/2 is minus 2. So this vector here, which is my W1, is minus 6 times m sub I plus minus 4 times m sub j, right? Those coefficients are the solution to this set of equations. So minus 6 times minus 3 gives me 18. Minus 4 times 1/2 gives me the minus 2. So this vector over in the domain, minus 6 minus 4, should give me the solution to this equation. And sure enough, if I take this vector, its x component is minus 6. If I flip that over the y-axis, that makes it 6, and then stretch it out, that gives me a component of 18. Its y component is minus 4. If I shrink that by in half, which is what the function does to the 1/2, it actually brings you to minus 2. So these two numbers, you can think of this in a couple of different ways. One is it's the vector minus 6i minus 4j in the domain that gets turned into the vector minus 6mi plus minus 4mj, and that's the vector 18 minus 2. And this vector here and these two vectors, the I and the j, have the same relationship as this column and this column due to 18 minus 2. So here's a different matrix, 2 minus 1 minus 4, 2. So what's m sub I? Well, that's the first column, so we're not going to actually write it out. The multiplication, m sub j, is the second column. That's minus 4, 2. So the function takes I and j, those two, and turns them into 2 minus 1, so 1, 2 minus 1, and that's m sub I, and minus 4, 2. 2, 3, 4, 1, 2, out there. That's m sub j, right? And by now we know that this vector times minus 2 gives you that vector. In fact, these two vectors have the same span, right? Which is the same thing as saying they're linearly dependent, right? In fact, mj is just minus 2 times mi. So what does our function actually do? Well, it takes whatever vector you want, right? V equals k1i plus k2j. And what does it do? It takes the m times v is going to be k1 times mi plus k2 times mj. Where is that going to land you? Well, k1 times mi, that lands you somewhere on this line. And then k2 times mj lands you somewhere on this line as well. So the sum is also on this line. So the entire line, the entire plane, is mapped to one dimension, just one line. Why is the range only part of the codomain? The range is this line. The codomain is the entire plane. Right? So if we take a vector that's not on that line, this vector would be a vector that's in the codomain but not in the range. So here are two examples. W2 is 6 minus 3, W3 is 2, 2. So we think of this again as being an arrangement in the codomain, and this is being an arrangement in the range, in the domain. So what do we have here? If we look at 6 minus 3, we know that this vector is just 3 times this vector. And that correspondence holds here as well. This vector, 2 minus 1, multiplied by 3, you get 6 minus 3. So over in the domain, we have I, and we have J, and we have a vector that's 3 times I. That's this column. And when we map that over to codomain, well, M times I is a vector 2 minus 1, like that. And M times, well, this is W2, right? Over in our codomain is just 6 times minus 3, and it's just 6 times that. 3 times that. So, what's that telling us about what's going on? MI, I keep writing J's and survives. So, we actually don't need this vector, right? The second vector, because it's multiple of the first vector. So we can actually describe the entire map by just looking at where I goes. So, what are all the possible vectors here? Well, we know that W2 equals 6 minus 3. Oh, hang on 1 second. Let me check my notes. Okay, so what do we know? We know that W2 is 3 times V1, right? And V1 is the vector, V2, sorry. And V2 is this vector, it's 3I. All right, hang on a second. Let me just undo some stuff there. 1, 2, 3. V2, W2 is actually 3 times I. W2 is 3 times MI over here. And so that means that V2 equal to 3 times I is multiplied, when this is multiplied by M, you get this. So W2 equals M times 3I. Good. But what we also know from this is that V2 is minus 2 V1. Let me stop for a second again and check my notes. Okay. So what we'll do is we'll say that we'll rewrite our, because our notation is getting a little messy here. This is minus 4, 2. This is 6 minus 3. I'm going to call this vector V1 and this vector V2, and this vector is W2. And this is all in the codomain. And we know that W2 equals 3 times V1. Well, we also know, we'll put a semicolon here from the reduced row echelon form, which is 1 minus 2, 0, 0. 0 is that v1, 2v1 plus v2 equals 0. So if I take twice this vector and that vector, what do I get? I get 0. Now that's a surprisingly interesting thing because W2 can be rewritten as 3 times V1 plus 0, which is the same thing as 3V1 plus 2V1 plus V2, right? Because that's equal to the 0 vector. And in fact, since this is a 0 vector, I can multiply it by any constant I want, and it's still 0. So what do we get then is that W2 can be written as V1 times 3 plus 2k plus V2 times k, right? Distribute this k, you get a 2k V1 and a 2k V2. So no matter what k value I pick, I can get a solution in terms of V1 and V2. And why can I do that? Because there's a linear dependence between those, right? And so there's infinitely many solutions, and you can write down what they are. When we're looking at this one, though, this equation boils down to saying that this vector and these two vectors are linearly dependent, but that this one is actually linearly independent of both of those. And so that's a way to interpret that, right? That this vector here is actually linearly independent of either one of these. It's not in their span. And so there's no solution because this vector here is not in the span of those, just as this vector here is not in the span of these two. So this equation where you get 0, 0 equals to 1, essentially, because it's an augmented matrix, that tells you there's no solution because the answer you're looking for isn't in the span of the columns. And so that tells us what's going on here. Infinitely many solutions is because V1 and V2 are literally dependent. No solutions because W3 is actually independent of the two column vectors V1 and V2. So summaries, if you have a 2 by 2 matrix M, Mi and Mj are the columns of the matrix. You can read through all this. It's there. If they're linearly independent columns, then the range equals the codomain, and you have exactly one vector in the V. In fact, the function is 1-to-1 onto. If the columns are not linearly independent, then you have a problem because then you can have infinitely many solutions, or if a vector is not in the span of the columns, then you have no solutions. So 3 by 3, same kind of thing. What does this reduced row echelon form tell us about these three vectors? So V1, V2, V3 are the column vectors. These are in the codomain. They're linearly independent. The codomain is, in this case, R3, because we're dealing with three-dimensional vectors. They're linearly independent. There's three of them. So the column vectors here span the codomain. And the idea being then that you're going to have, now in 3 dimensions, you'll have I, J, and K. And that maps over to, I don't know, V1, V2, and V3. But these are linearly independent, so it actually spans the whole thing. It's easier to actually have GeoGebra create some pictures of this. So here's the geometry of the function using the domains, using the diagrams where this is our vector. So This is in the domain. Red here is the x-axis. This is I. J is the little green arrow, and K is the little blue arrow. And this is our vector 2 minus 2, 3. And so you can see that it's 2 units in the x direction, minus 2 units in the y direction, and then 3 units up in the z direction. So red is x, green is y, blue is z. So over the codomain, what do we get? Well, let's zoom out a little bit so we can see some of these pictures. What our matrix does is it takes this picture and it turns it into this picture. So the little red arrow here, which is I, gets turned into this longer red arrow. That's the image m times I. And green turns into green, and blue turns into blue. And the black vector gets transported into this thing. And it's dotted because it's actually under that plane. It's under the xy plane. But the relationship between the vectors, right? A certain distance this way, a certain distance this way. This is 2 minus 2. And what was the last number? 3? 3. Stays the same, right? We go 2 units in the red direction, then we go minus 2 units in the green direction. This and this are actually parallel. So minus 2 direction in the green direction, and then we go 3 in the blue direction. And that tells us where our image vector ends up. So I always think of this as IJK as being sort of the skeleton of the transformation. You see where those go, and then it just drags everything with it, right? The black vector has a particular relationship to IJK. That same relationship holds with the relative to the images of IJ and K in the third dimensions. So what's W? Right? So M times 2 minus 2, 3 is this whole matrix 4, 3 minus 4, 1 minus 1, 1, 0, 2, 1 times 2 minus 2, 3. And that gets mapped onto this vector if you multiply it all out, which I'm not going to do. The reduced for echelon form tells us that this is the solution to that, which isn't surprising. Right? We started with the solution, and then we figured out what the numbers on the right-hand side have to be. So there aren't any other functions that get mapped there because these three are linearly independent, and there's only one way to get to W using these three vectors, and it's 2 in this direction, minus 2 in that direction, 3 in that direction. So here's a second example. Here's the RREF. What does that tell us about the function? Well, here, M sub I, M sub J are linearly independent, but M sub K, not M sub K, M times K, is actually linearly dependent on Mi and Mj. So if we call this, sometimes a little easier to call this vectors V1, V2, and V3, that's our column vectors. What do we actually have here? V3 equals 3 times V1 minus V2, or 3V1 minus V2 minus V3 equals the 0 vector. And this is going to turn out to give us multiple solutions again, right? We have 2 linearly independent vectors and a linearly dependent one. Here's a dependency relationship. So we can get infinitely many solutions. What it suggests, though, is that our function, whatever this function is going to start in 3 dimensions with I, J, and K as being separate things. And then we're going to end up with going to 3 dimensions again with M sub I and M sub J, wherever they are, and they're going to span a plane. And M sub K is going to be in that plane. So the span of this, the range, will be two-dimensional. We're losing a dimension along the way. So V is 1, 2, 1. W is 7 minus 6, 6. Use the pictures blue to explain the geometry of this. So we're actually doing the codomain here. And again, red is m times I. Green is m times j. And blue is m times k. And all three of these vectors lie in this one plane. And so when we take m times the vector 1, 2, 1, we get another vector, the black vector. This is w. But that's a linear combination of these three. The span of these three is this blue plane. So this black vector lies in that blue plane as well. So m of 1, 2, 1 equals 7 minus 6, 6, because we go 1 unit in the red direction, 2 units in the green direction, and then 1 unit in the blue direction, and that gives us our black vector. But we can represent it a different way because we don't actually need V3, right? V3 is a linear combination of V1 and V2. So we can get to that tip of that black vector just by going 4 units times mj, that's here, not mj, mi. I don't know why I keep saying j instead of I. 4 times m times I, that's this direction, plus 1 times m times j. That's this direction. And that gets us to the tip of the black vector as well. So it's two different solutions to having an output of 7 minus 6, 6. So two different vectors, both of them go to 7 minus 6, 6. What are all the possible solutions? Well, again, we use our reduced echelon form here, right? This is 7 minus 6, 6. We know that seven minus 6, 6 equals, if this is vector v1 and this is vector v2, will equal 4 times vector 1 plus 1 times vector 2, plus sign. Or if we're calling this W, I think we're calling that W. 7 minus, I'm going to call it W. If we call this W, W equals 4 times V1 plus V2. But we know from up here, way up here, way up here apparently, 3V1 minus V2 minus V3 equals 0. And we actually knew that from this. So 3V1 minus V2 minus V3 equals 0, the 0 vector. Because this vector here, which is V3, is equal to 3 times V1 minus V2. So 3V1 minus V2 minus V3 equals 0. So what is W? W is 4V1 plus V2 plus, well, this is the 0 vector, so adding the 0 vector on doesn't change anything. And multiplying a 0 vector by a constant doesn't change anything either. It's still just 0. So W can be rewritten like that. And we can think of this again, if we wanted to, as this as being a particular solution, and this is being homogeneous. And again, we'll see that in next week's videos, but also you can rearrange this, regroup by vectors. V1, what's the coefficients? You got a 4 there. You've got a 3k over here. plus v2, you've got a coefficient of 1 here, and a minus 1 times k there, plus v3, 2 there, and you've got a coefficient of just k minus k. So any choice of k, any real number, will give you a solution. So you have infinitely many solutions. So what's a vector that's in the codomain but not in the range? Well, there's lots, right? This is one example, 1, 0, 0. That's in the codomain but not in the range, because if we looked at the Roman-reduced echelon form, it's telling us that this vector here, this column vector, is linearly independent of these vectors. So this column vector is linearly independent of those vectors, which means that this vector is not in the span of these things, which means it's not in the codomain. It's not in the range of the function. And so we can do these much bigger things if we wanted to. Here's a big complicated function. We're going from 10 dimensions down to 7. So 1, 2, 3, 4, let's see, 1, 2, 3, 4, 5, 6, 7, 10 vectors in a 7-dimensional space. We know at least 3 of them have to be linearly dependent on the others, but v1 and v2 are linearly independent. v3 depends on v1 and v2. v3 and v4 are linearly independent of v1 and v2. But v5 depends on v1 and on v3 and on v4. v6 and v7 are linearly independent, but v8, the 1 and 1 here, depends on v6 and v7, and v9 depends on v1, v6, and v7. So we actually have 1, 2, 3, 4, 5, 6 linearly independent. So we're going to codomain equals R7, but range is 6-dimensional because we only have 6 linearly independent vectors. So what does that mean? Well, we're going to have 4 parameters. Right up here, we just had 1 parameter. We just had the k. But here we're actually going to end up with 4 parameters because we have 4 dependencies. And those 4 vectors, right, we started out in 10 dimensions, and we went down to a 6-dimensional range. And so those 4 vectors are sort of the 4 dimensions that we lost along the way. And so we end up with a 6-dimensional space inside of 7-dimensional space. There will be vectors that are in the codomain, but not in the span, because they just point off of that. And so we will talk some more about this next week. And we'll also talk about eigenvalues and what all this has to do with differentiation.